The next part of our lecture is the case of a temporary moment. We said that in a temporary moment we do not know the direction. The direction will come in one direction and it may come in the opposite, completely opposite direction. But anyway, when it comes from any direction, I will have this shape. This shape represents a 3D for the stress below the footing. The stress below the footing will be maximum at one location and minimum in the other location. If you go to the this section below, you will find that the moment is different. Here it is the maximum, here it is the minimum, here is the minimum, here it is the maximum, because as I said, it is not fixed in direction. It may be the opposite. We will just take this example in principle. We are not going to substitute by numbers. You remember when we came to calculate the bending moment on a footing, the bending moment on the footing was was affected by, as we said, if you remember, W actual, and we said W actual, we take the normal force of the column, divide it by the area, the actual area of the footing, to get the stress. Here the stress is variable. So if I take this case, or I take this case first, if I take this case, do you consider which cantilever to be critical? This one or this one? Take this example here. I have maximum stress here, minimum stress here. Critical means a bigger moment. Which one will give you the biggest moment on this one? Because it has the higher stress. It's normal. Okay, this is, we'll take this. This is the portion of the stress that will make the moment. The F maximum here is this F maximum. But we only took the stresses till the edge of the column. So I take this here, and this is not uniform. The stress is not uniform. It is here very high value, here less value. So I have to get the CG of the load and the resultant, the CG of the stress and the resultant of the stress, because I need to replace this stress with one force to get the effect of the moment. You remember this from the structural data. If I want to know what is the moment due to these stresses, I just replace them with a resultant force, calculate the resultant force, get the point of application. It will be at a distance of Z1 from the edge of the column. Then the moment they make is the effect of this force multiplied by Z. In this case, I will get the moment of this cantilever. Should I calculate the moment of the other cantilever? No. Why? First, because it will be less. Second, it may be less and I calculate it because I will need it to get the amount of steel. But here I don't have a separate amount of steel because the reinforcement here will continue to be in the other side. So if I need here, say, 5 rebars per meter, phi 22, I cannot make them phi 16 in the other direction. They will continue phi 22. So I will not calculate this because I don't need it. But I may calculate the perpendicular direction because there is another set of reinforcement in the perpendicular direction. This I will check which one is the critical cantilever, and in my case, because I have moment in one direction, so in the other direction I have both cantilevers of the same length. Anyway, we'll just concentrate now on this direction. So I can get the moment, which will be M1 for this cantilever. I go to this is what I was saying. Here I calculated the moment in this direction. Let's calculate the moment in the perpendicular direction. In the perpendicular direction, imagine that you splitted part of the footing, the cantilever, you splitted it away, and this is the stress below the cantilever. The stress below the cantilever is maximum from one side and minimum from the other side. So you have to replace this shape with just one moment at a distance of Z2 from the edge of the column. And so you will calculate M2. So you will have M1 in the long direction and M2 in the short direction. Based on M1 and M2, you of course you are going to use M1 because it is the bigger one, or it may be the other. It depends on the shape of the problem, but usually it is M1 that is bigger. I take M1 and I use it in this equation to get the D, and then add 7 centimeters to get the required amount of reinforcement per meter, because we are studying if this distance is 4 meters. I have two options: either to get the moment due to the 4 meters, and when I get the amount of steel, I know that the amount of steel I calculated was for the 4 meters, or I just take a strip 1 meter. But in this case, I cannot take a strip. Why? Because this strip has a moment different than this one, because the stress is different. Maybe here I can take a strip, because if this distance is 2 meters, the portion of the first meter is exactly the same as the second meter, because they both check the drawing. If you look at the drawing, you will find that each centimeter of this strip has the same feature. It starts with the maximum and ends up with a value less than the maximum. But if you take this direction, each centimeter is different than the other. Here it is fully maximum, and here it is fully minimum. So anyway, you need, as a general rule, either you calculate the moment due to the full width of the footing, and in this case, when you get the moment, just divided by the length of the footing to get the amount required per meter. Or you just, if you can use each meter similar to this direction, if you can do it by meter, it's okay, never mind. What is important, what you are going to write on your drawing. If I say here, this is my drawing. Where is the drawing here? This one. Here it says 6 phi 18 per meter. So I'm giving you per meter. If I just tell you, no, it is not 6 phi 18 per meter, I know that this is 3.2 meters. If I multiply 3.2 by 6, it will be something like 20 rebars, and I will just say that from this point till this point I have 20 reinforcements. You follow this, or I repeat it again? It's either you give me on any footing the amount per meter. If I have a footing 4 by 3, in the 4 meters I have 20 rebars. So 20 by 4, so it is 5 by meter. Either on the drawing you write 5 rebars per meter, or you write 20 rebars from edge to edge. Like what you do in beams. In a beam, you don't write the reinforcement per meter, because the width of the beam is 30 centimeter or something. So you just put the full amount. So in footings, we may have two options. Either write the amount directly from edge to edge. You say that you have 20 rebars here. Or you say that it is 5 rebars per meter. It's the same, and it differs from one place to the other. In some places they prefer to write per meter, and in some other places they prefer to write the full number because it helps in construction. If you tell me the full number, then I don't have to calculate it, because maybe if you give me per meter and I come to calculate multiply by the width, then I would have 20 rebars 0.5. So I will use 20 or 21. It is better that I would give the total for the contractor. But both are okay and both are the same, and whoever will check it, he's an engineer, he can give decision, and it's okay. We'll go back to our here we said that this is the first moment, this is the second moment. So if I have the first moment and the second moment, I will take the maximum, calculate the depth. From the depth I calculate the T, then I go to the check of shear. It will be the same as before, but the value of the force will differ. Because if I'm taking the force here is not, the force causing the shear is not uniform, it is also maximum in one direction, minimum in the other. So I will calculate the shear based on my new stresses, and I will compare it to the allowable given in the code. I will check punching with the same way, and then after I check punching, then if it is okay shear and punching, then I would go and calculate the amount of steel and put the amount of steel, and finally I put my reinforcement. And as you see, my reinforcement will be similar to an isolated footing without moment, but the difference, the real difference will be in the amount of steel. It will be very high amount of steel, but the column will be in the middle. I cannot from here I will not know that I have a moment, because it's a normal column in the middle, it is not shifted. But when I look at the amount of reinforcement and I find it very high, I expect that there was moment additionally plus the normal force. This is the shape of the reinforcement. You see here, you remember in the previous one it was U-shaped. And in this case it is not U-shaped, it is U-shape but with one side. We call it forks in Arabic, shawak. Why do we use this or we use a U-shape? When the footing is small and the amount of reinforcement is small, then I use the U-shape. But if I have, like this case, I have moment in both directions, so I have a lot of steel. You remember in beams, we used to have something called curtailment of steel. Do you remember what is curtailment of steel? It's something to reduce the amount of steel. If I have, say, a beam, in the middle of the beam I have very high bending moment, so I need 10 rebars. But if I go to the middle, say a little bit to the right and a little bit to the left, then I don't need the 10, I may need 5 or I may less. So I make something called curtailment. Curtailment means that I do not extend the full amount of steel from the edge to the edge. I use part of the steel to be maybe covering an area, and then the other will be covering a bigger area, and so on, so that if I check the section of the beam in the middle, it will contain 10 rebars. If I check the section of the beam near the columns, it will be maybe 5 rebars or 6 rebars. So I managed to reduce 4 rebars as a way to reduce the cost. In this case, also we use this. Instead of using a U-shaped, I can use it with one side only, and the other one will have the side, the opposite side. Here I have this side, the next one will be with the side here. So in this case, I reduce this. Here I have a side, here I don't have a side. So I reduce one side, each rebar. I don't need really all of this amount, so I'm reducing it. It's a way for cost reduction, and that's all, because I don't need all the amount of steel to reach from the start till the end of the reinforcement. يعني both are okay. Usually we do 50% this shape and the other 50% of the other shape. So we use this in case we have very high amount of steel and we want to make some cost reduction. If I don't have I don't need to do cost reduction and the amount of steel is okay, then I can use U-shape. This is the case that I was discussing with you. Suppose I have moment in X and Y direction. This is what I wanted to calculate. I will just calculate the eccentricity due to X, which is mx divided by the normal force, and I will calculate the eccentricity due to my, which is my divided by the normal force. So I have now two eccentricities. I need to shift the column twice, one with ex and one with ey. So you start, this is the middle point, take this ex and then go down ey, or the opposite, start from here, take ey, then ex. This will be the new center of the column. If I manage to do this, then it will be similar to the isolated footing, but with shifted column in both directions. That's all. This is the only difference. Finally, just some cases of loading for to understand all the expected loading. In case I have a temporary moment, which means that it is variable, then it is not in one direction, it is in both directions. In this case, the moment, this one, I have a temporary moment. This was, in case we have moment in X and Y direction. If it is permanent, then I can shift the column. If it is not permanent, similar to the previous case we studied, no, I cannot shift the column. But in this case, the stresses will be MS, because I will have 4 different values for stresses, something like this, F1, F2, F3, F4. And they may have negative values. So it is I may have a negative value here. In this case, I will have to redistribute the stresses again. And if I show you, I did not put it here, but if I show you the equation that I used to get the value of the moment, it's very long with lots of parameters, lots of numbers. The possibility of making mistakes is very, very high. So it is not something that we expect to see in a limited time exam. But it is something that you may face in a project, in a coursework. You can do this. If you do something like this, then you're doing something very, very good. But for the time being, usually in offices and design offices, if we have something like this, we prefer to solve it using a computer program, because it will minimize the errors, the human errors, which will be high in this example. So these are the shapes. This is a summary of in case I have moment in mx and my, in case I have moment in mx or my. So just a summary in one slide to see the difference. Here I have moment in one direction, so I have f maximum in direction and f minimum in the other. If I have moment in two directions, then I will have four different values, f1, f2, f3, f4, and one of them, or maybe two, or maybe three, may be negative, depending on the intensity of the moments. This is a summary. As I said, this ends up the lecture, but as I said, this case with variable moment is a little bit complicated, so we have to know it in case we face it in the future. We can solve it, but we have to concentrate to minimize our expected errors. This ends up our lecture. Thank you very much, and see you next week.